Hello guys, in this video we will solve a problem related to insulated strings in overhead transmission lines. As you can see in this figure, in this image, we have overhead transmission line conductors. As you can see, these are our conductors. These conductors are usually very heavy and they are thick and they are very long. So they have a significant mass. Therefore, we need such kind of insulators which are mechanically strong enough to support these conductors with the towers and also which can provide a significant dielectric strength such that there will be no flashover from the conductors to the tower. And one choice is string insulators. Insulators are composed of multiple disks which are connected together to make a string. And these disks are usually made up of either toughened glass or porcelain material. So we are gonna now we are gonna discuss the problem related to string insulators. So we are not going into the detail of the porcelain or the glass insulator materials. That is another topic. So let's start here. In this problem, we are given 33 kV overhead line and there are three units in a string of insulators. So there are three disks which are making a string. And if the capacitance between each insulator pin and the earth is 11% of the self-capacitance of insulator, find the distribution of voltage over the three insulators and string efficiency. So before we proceed to the solution, we need to understand the problem well. So I'm going to redraw the tower. So this is our tower. And then we have on the cross arm, we have three disks which are connected together to make a string. And then we have the line. So this is our line. These are our three disks. This is our string insulator made from three disks. Okay, and this is tower. And tower is at ground potential. Okay, so if we draw its electrical equivalent diagram, it will look something like this. We have our structure, which is at ground potential or zero potential, and then we have capacitance of one disk, capacitance of another disk, and capacitance of the third disk. As you know, all the insulators can be modeled as a capacitance. Sometimes we put conductance in parallel with the capacitance, but conductance is really negligible. So most of the time we ignore the conductance. So here we have the capacitance of the disks, and we say that they are identical disks and their capacitance of each of the disk is C. And here we have line. Here we have line connected. Okay, then also we will have capacitance naturally whenever we have difference of potential, whenever we have high potential and low potential, and we have air in between, naturally it forms a capacitor as well. So here we call it CE, earth capacitance. Okay. Okay. So now, okay. So now we are given the condition here. We are given 33 kV line. So most of the times, or always when we talk about three-phase system, we are given three-phase line-to-line voltage. So this is line to line voltage. Okay. And but now here we are talking about only one phase. So we will convert it into phase voltage, V phase. So the voltage between the line and the tower will be phase voltage. We call it VPH. Okay, and then the voltage across each of the insulator, we can label them. For example, this is V1 and this is V2 across the second unit, and this is V3 across the third unit. And what else is given? We are given that the capacitance between each insulator pin and earth is 11% of the self-capacitance of each insulator, which means this capacitance, what we labeled as CE, earth capacitance, is actually 11% of the self-capacitance of the disks, or the capacitance of the disks. So which means this is 0.11 times C. So the capacitance of this capacitor CE, earth capacitor, which is the capacitance between the pin of the insulator and the ground or the tower. So this is how we labeled. Now we need to determine this. Our objective is to determine V1, V2, and V3. This is our first part. In second part, we need to determine the string efficiency. And string efficiency is given by phase voltage divided by N times the voltage across the insulator, which is next to the line, which is V3. And N is the number of insulator units in the string. Okay. So in this case, we have 3 units. Okay, now we are going to apply circuit analysis techniques to determine the values of V1, V2, and V3. So let's start. First, we will label the currents. Let's suppose the currents flowing through each of them are, let's suppose this one is this is my, let's start from the top. So this current flowing here is my, let's suppose I1, and current flowing here is I1 bar. This is I2, and this current is I2 bar. This current is I3. This is I3 bar. Okay, so we labeled the currents. Now let's label the nodes. How many nodes do we have? We have, this is my node A, and this is my node B. Okay, so now our total phase voltage applied across the whole string is V phase, and this is equal to actually the sum of all the voltages V1, plus V2 plus V3. And this V phase is equal to line voltage divided by square root of 3. And line to line voltage in this question is given as, you can see, 33 kV divided by square root of 3, and this will give us 19.05 kilovolt. Okay, so this is our first equation. We can write it also here. V1 plus V2 plus V3 is equal to 19.05 kilovolt. This is my equation 1. Okay. Now I will apply KCL, Kirchhoff's current law, at node A. As you can see here, at node A, my entering current is I2 and my leaving currents are I1 and I1 bar. So I'm KCL at node A. As I said, I2 will be equal to I1 plus I1 bar. I1 bar is the current which flows through the earth capacitance, as you can see, and I1 is the current which flows through the capacitance C. As you know from Ohm's law, current is equal to V over the impedance. Okay. Now here we are talking about capacitors. So impedance of a capacitor ZC is equal to 1 over j omega C. Okay, so current through any capacitor will be equal to V multiplied by j omega C. So we will use this rule to, to put the values, to put the expressions for I1, I1 bar and I2. So I2, what is the voltage across across the, so I2 is the current which flows through, as you can see, it flows through this middle unit, and the voltage across this is V2, as you can see, and its capacitance is C. So we will use this. So I1 is I2 is equal to V2 times j omega C, and this is equal to I1. As you can see here, I1 is the current which flows through this unit. Okay, and capacitance of this unit is C, and the voltage across this is V1. Therefore, what will be current I1? I1 will be equal to Ohm's law, voltage across it multiplied by j omega C. So it will be voltage across it is V1 and multiplied by j omega C, plus, now we have I1. I1 is the current which flows through this unit, I1 bar. I1 bar is the current which flows through the earth capacitance. And the value of capacitance is 0.11 C, as you can see. So the current flowing will be voltage across this, and voltage across it, as you can see, this whole tower is at ground potential, is at the same potential. So this node and this node, they are at the same potential. So this node is common between the self capacitance and between the earth capacitance. So the voltage across CE and this top capacitance C will be equal. Hence, the voltage across both of these capacitances will be V1, and the voltage, therefore, the voltage across CE will be V1 in this case, in which we are interested. So now we will have V1, and voltage across the earth capacitance was V1, and it was j omega, and the capacitance was 0.11 times C. Okay. So we will now reduce this equation. So as we can see, j omega is common in all of these terms. So we will cancel j omega, and C is also common. So we will cross C as well. So now we can write V2 is equal to V1 plus 0.11 times V1, and we can further simplify it. It will be 1.11 times V1. Okay, so we got a relationship between V1 and V2. Now, similarly, we will write KCL equation at node B. So for node B, we can see the entering current is I3, and the leaving currents are I2 bar and I2. Okay, so in this case, I3 will be equal to I2 plus I2 bar. So that's what I'm going to write here. I can name this previous equation as equation number 2. So now I3 will be equal to I2 plus I2 bar. Okay, now I3 will be again equal to the voltage across this unit, which is V3 multiplied by j omega C. C is the capacitance of this unit. And similarly, I2 will be the voltage across this second capacitance, which is V2 multiplied by j omega C. Now I2 bar is this current which flows through this branch, which flows through this capacitance. Now how much is the voltage across this one? That's a little bit tricky to find out. You can see this node here, this node here, which is my node B, the voltage between this node and ground, this is my ground, and the potential at this node is 0. So now the voltage between node B and the ground, if we look up, we can see this is simply sum of V1 and V2. So voltage from here to the top node is V1 plus V2. As we can see, our tower is at the same potential. So this node will also be at the ground potential. So the voltage across this one, across this insulator, will be same as the voltage if we look straight up, it was V1 plus V2. So we will write here, again we are gonna start from I3. I3 we said earlier, it is V3 and j omega C, and I2 is the current through the middle insulator, and voltage across that is V2 and j omega C again, plus now I2 bar is the current through this earth capacitance, and voltage across it, as we said, it is V1 plus V2 multiplied by j omega 0.11 c. Okay, so we can again cross j omega c here, j omega c here, and j omega and c here. So we can simplify it as v3 is equal to v2 plus 0.11 times v1. If we multiply this 0.11 with v1 and v2 both, plus 0.11 times v2. Okay, then I can plug the value of v2 which I determined previously from equation number 2. So v3 will be equal to 1.11 times v1, which is the value of v2, plus 0.11 v1 plus 0.11, and the value of v2 was 1.11 v1. Okay, now if we add them up, multiply these and then add all these terms, we will get v3 equal to 1.342 v1. This is my third equation. So now I got v2 is equal to 1.11 times v1 and v3 is equal to 1.342 times v1. If we plug these values in this equation, in equation number 1, I will get the value of v1. So v1 plus v2 plus v3 is equal to 19.05 kilovolt. So v1, keep it as v1. v2, we will plug the value of v2 which we determined earlier, which was 1.11 v1, plus v3, it will be 1.342 v1, and this is equal to 19.05 kilovolt. So now v1 will be equal to, if we solve this, so v1 will be equal to 5.52 kilovolt. Okay, so v2 will be equal to 1.11 times v1, and if we put the value of v1 5.52, so I will get 6.13 kilovolt. Similarly, v3 is equal to 1.342 from equation number 3, 1.342 times v1, and if we plug the value of v1, I will get 7.40 kilovolt. Okay, we can cross check if our solution is correct or not. You can add v1, v2 and v3, and the sum must be equal to 19.5 kilovolt. Okay, now you can see how the voltage is distributed across the three discs in our string insulator. And then we can, in part B, we were required to find the string efficiency. We can calculate the string efficiency, which was equal to V phase divided by number of number of discs in a string, which is 3 times V3. So multiplied by 100 to get it into percent. So V phase is 19.05 multiplied by 100 divided by 3 times, and V3 is 7.4, and in this way efficiency will be equal to 85.8%. So efficiency actually indicates how homogeneously the voltage is distributed across all the disks in a string insulator. If string efficiency is 100%, that means the voltage across all the disks is equal. If efficiency is less than 50%, for example, then the voltage distribution is really non-homogeneous, which is a bad design. So in this way, it is 85.8, so which is quite fine. Okay, that's all. Thank you.